Good morning. Hey guys, and welcome back to another great Wednesday. It's actually cleared up now and sunny outside, so let's go ahead and learn about some taxonomy. So today we're going to go ahead and apply what we learned in our cladistics and taxonomy lesson from last time, the two major branches of classification in evolutionary biology. And today we're going to go ahead and use the two biggest tools of classifying biologists, which are the cladogram and the dichotomous key. So we're going to learn how to read both of those and to make both of those, and that's going to be the applied portion of the lab for today. Let's go ahead and dive in. I actually want to start by showing you something called Deep Tree. This is something that PBS and NOVA came up with, and Deep Tree is a program that is basically an interactive cladogram that has all of these different species that are plugged into it. And so what does this mean? Well, this is basically the tree of life. It is all of the known connections and interconnections between organisms that we've been able to come up with based off of those homologous features, that DNA evidence that we know of, and all of that stuff. So this is what we currently know of the tree of life, and it was created by classifying and evolutionary biologists. So what if I wanted to see the evolutionary relationships and lineage of the common domestic cat? So here's domesticated cats, Felis catus. What if I wanted to know? Well, I would click on that in this, and it would show me the evolutionary history of the cat. All of the branches of organisms that that cat is related to. And look at that. Oh, there were all those little fishopods that we had been talking about previously. And then my computer is probably not powerful enough to be able to run this very well. But hopefully what you're able to see here is just the incredible size of the tree of life, the sheer number of species that are related to each other and interrelated in all of these cladograms, these branches of life. And here we go, we're getting into mammals now, we're getting closer and closer, and there's the cat with its most common ancestor right about here to all of these other species of cat besides the domesticated cat. We have Felis chaus, which is the jungle cat, or Felis manual, which is the, I can't even read that, the something cat. Then we have the Chinese mountain cat, Felis beatty, so, or Betty. So that's really awesome. This is a really cool program. I'll put a link to it and for you guys to take a look at it. But it's really cool, and it really gives you perspective on what we're able to see using this cladogram. And I can actually zoom out at will and go all the way back and do that whole thing again. But just incredible to see how many different trees we've been able to come up with as we classify organisms based off of their evolutionary relationships. So I just wanted to show that to you. It's really cool. So now we're going to move on to reading cladograms. So we talked about this a little bit before, but reading a cladogram is a map that essentially shows you traits when they have evolved in the evolutionary lineage and what organisms were a product of the evolution of those traits. So if we look over here, when lungs evolved, that allowed for things like salamanders and lizards and pigeons and mice and chimps to evolve because they're all terrestrial, land-walking organisms that breathe air. But before lungs evolved, that's when we had the perch and the hagfish. So we had a bunch of things that were living in the ocean and they couldn't breathe on the air. They didn't have lungs yet. And then we have things like feathers, okay? Feathers evolve right here, and that allows for the pigeon. Before that, there weren't feathers. And then we have fur evolving over here, and that allows for mammals like mice and chimps, but before that, nobody has fur. So when you look at a cladogram, how you read it is you go to the trait, and anything to the left of that trait doesn't have it, and anything to the right of that trait does. So none of these, salamander, perch, nor hagfish, have claws or nails, but lizards, pigeons, mice, and chimps do have claws and nails. So that's awesome. Over here, you can see the same thing. The evolution of the jaw allowed for the tuna, salamander, turtle, leopard. Before that, we had the lamprey and the lancelet. And then, of course, hair allowed for the leopard. Nobody else has hair over here. So this is just a cool way for us to be able to map, and really what Deep Tree is, what we were looking at before, this is just a cladogram that has been constructed based off of those homologous features, right? So fur and mammary glands are homologous anatomical features shared by the mouse and the chimp. Claws and nails are anatomical features shared by all of these. So these are those homologous structures we were talking about. We can also use DNA evidence to build these trees, which is what deep tree is also partially based on. So that's how you read a cladogram. How do you make one? Well, making a cladogram, usually what happens is you're given a list of species and their traits. So here we have shark, bullfrog, kangaroo, and human. And we're given traits here that they might all share. So vertebrae, 2 pairs of limbs, mammary glands, and a placenta. Here, what we can see, the X's are marking what traits that each of these species actually has. So the shark only has a vertebrae, which is a backbone. It doesn't have 2 pairs of limbs, mammary glands, or placenta. On the other hand, the human has all of them. It has all of these traits. So how would we build a cladogram out of this? Well, what we would do is we go ahead and count the number of organisms we have. So 1, 2, 3, 4. Okay, and I'm going to draw a backbone for this cladogram, and I need 4 branches in the end. And we're going to count this as one of the branches. So I really need 3 coming off this. So I'm going to do 1, 2, and 3. And the idea is to have them all roughly the same length when if you were to take like a line and draw a line across right here, they should all be the same length. You can see this one's right about here. I've tried to stop them all at that space. And the reason why is that the length of the lines coming off of a cladogram indicate how long that species has lived. So all of these species right here, the hagfish have been around on Earth for a lot longer than the chimp has. We've been around even shorter amount of time than the chimps have been, right? But this line tells us the hagfish has lived a really long time. The fact that all of these lines are relatively equal, though, that they are happening at about the same place, means that they're all living at the same time together. This one here isn't, this is a little bit of an anomaly, but in a good cladogram, we can see they're all about the same length because it means that they're all living on the Earth at the same time. However, the cladogram shows that lancelets evolved a lot longer ago. So while, yes, they are still living with us, they have been here a lot longer than leopards have, or turtles, or salamanders, etc. So that's what we're showing here with those lines. That's why it's important to keep them the same length. So then what I need to figure out is which one is my outgroup. So when I'm looking at this, okay, so sorry, hang on. First I need to put my traits on. So the first trait I'm going to put on is shared by everybody. So I'm going to put it to the left of everybody else because remember, for a trait to be had, it has to be to the right of when that trait evolved, right? So if we have a vertebrae, everything to the right of that will have the vertebrae. So I'm going to go ahead and put my vertebrae down here. I'm going to type that in smaller down here. So this is my vertebrae, or my backbone. Okay, and that evolved here at this line. So everything to the right has that. Okay, so in the first organism to evolve after that occurred was my shark. So I'm going to put my shark right here. The shark's the first one to evolve after the evolution of the vertebrae. The second trait that I'm going to put on is 2 pairs of limbs, because I can see that that's the next one that's shared by the most organisms. So I'm going to go ahead and put that here. And I'm going to write that in. So I'm just going to say 2 pairs of limbs, like that. Okay, and the first organism to evolve after 2 pairs of limbs came along was my bullfrog. So I'm going to put my bullfrog right there. And I'm going to keep on in this manner. So I can see that the next trait that is shared by the most organisms is mammary glands. So I'm going to go ahead and write down here mam glands. I might just write down mam glands. And the first organism to evolve after that was the kangaroo. And then we have the placenta. So the placenta evolved after the kangaroo. I'm actually going to put the word down here for space, placenta. And here we get our human evolving after the placenta. So that's how I would make a cladogram based off of the information in this chart. Okay, so then what is a dichotomous key? So we talked briefly about the dichotomous key. It's a way for us to be able to look at an organism and to try to place it on one of these big trees based off of the features the organism has. So let's say we're an alien that's coming in, or maybe easier, let's say that we're a scientist who's never seen any of these organisms before, which is kind of hard to believe, but go with it. Scientists has never seen these organisms before, and so we're going to try to place them on this tree based off of the traits that they have, and we're going to have this handy-dandy little dichotomous key to do it. So dichotomous key, if we break it down, the di means 2. Okay, so we have two choices for each one of the traits that we looked at. And that's really what we're going to use here is sets of two choices to be able to narrow down our options to tell what is what. So let's say that I start over here with this, well, I don't know, it's a snake. I start with organism number 1. Okay, and I go over here and I say, does it have a backbone or does it not have a backbone? Now, the cool thing is I actually know that snakes do have a backbone. If you didn't know that, if that surprises you, go ahead and look up the skeleton of a snake. It's really wild. You'll also see that the snake skeleton has vestigial legs. Sorry, let's go ahead and look at this. I want you to see snake skeleton. This is really cool. So this is what the skeleton of a snake looks like. And actually, there's also usually vestigial legs that are coming out on these skeletons as well. And I'm not seeing it very much here, but let's see if we can see vestigial legs. Yeah, and so in snake skeletons, we can actually see down here, these are little vestigial legs that are left over that, of course, the snake doesn't have, but it suggests that its ancestors once had legs, which is pretty cool, and that they actually lost them. Interesting. Anyway, so we have this organism. We know it has a backbone, so I'm going to read 1A as backbone, and it says go to 2. It's kind of like a choose your own adventure story, so I'm going to go down to 2. I'm going to read 2A first. Okay, does it have wings? No. So then I go to 2B. No wings. It says go to 3. Okay, go to 3. Does it have legs? No, it doesn't. So no legs. Aha! We call this a snake. A snake. Woo! Yay, we identified the snake. Now we do the same thing for the lizard. So we go to the lizard and we say, okay, does it have a backbone? Yes. We go to 2. 2, does it have wings? No. No wings. Go to 3. 3. Does it have legs? Yes. Go to 4. Okay, 4. Does it have a shell? No. No shell. Lizard. Haha, it's a lizard. Waha! And you do the same thing for the turtle and the spider and the ant and the bat. So let's try the spider. Spider, does it have a backbone? Nope, it doesn't have a backbone. Go to 5. Does it have an antenna? Nope, don't see anything sticking off its head, so no antenna, it's a spider. Right, so this is how you use a dichotomous key. This is how you read one. Yeah, how do you make one? So I'm going to pretend, because I can't show you here physically, I'm going to pretend like I have these 3 pencils in front of me, wooden pencil, clutch pencil, and an automatic pencil. And now they're non-living things, but let's say that these were living organisms and I wanted to sort them based off of their features. I can make a dichotomous key. So making a dichotomous key, what you do is you first come up with a list. So I have 1A and 1B. Whoops. And then I have 2A and 2B. And 3A and 3B. I don't know if I'll need all these options, but I'm just kind of giving myself a large list to kind of work off of. So here are my sets of options, and now I need to figure out, okay, the first thing I need to do is I need to figure out a trait that can separate one of these out from the other one. I think I've got it. So this guy right here doesn't have these little clips. Right? Okay, and so this guy right here, I'm going to say, okay, it has clips, and if it has clips, go to 2. Okay, but if it doesn't have clips, it is the wooden pencil. Okay, now I need to find a trait that can separate these guys out. How about color? This one is blue and this one is silver. So over here, I could say for 2A is silver, and I could say it is the automatic pencil. For 2B, if it's blue, I could say the clutch pencil. And you can see I don't even need the third option there. And that's usually true. When you have a certain number of organisms, usually when you're making a dichotomous key, the number of steps you need is going to be one less than the number of organisms you have. So this right here, we can see I've got 3 organisms here. And that means 3 minus 2 is going to give me, excuse me, God, what am I doing? And that means, I'll just type it. And that means 3 minus 1 is going to be 2, and of course I ended up with 2 steps. So hopefully that helps you in doing your lab for today. That's all I'm going to talk about today is just how to make and use dichotomous keys and cladograms. I hope you've enjoyed, and I hope you enjoy your lab day and the sunshine. Make sure you're getting some sunshine. All right, guys, stay safe, stay well. Look forward to seeing you on Friday.